Hello, in the third lecture on power electronics, we will be studying about silicon control rectifier or SCR. Another name to use for SCR is thyristor. This is one of the most important switches. This is because it gives us one advantage that neither MOSFET nor BJT nor IGBT could give us. It can work with both AC and DC. In this lecture, we will be studying about the device physics of SCR, its circuit symbol and its IV characteristics. As we can see, the circuit symbol of SCR looks like a diode. It has an anode and cathode similar to diode. The only thing different is the gate terminal. This is the control terminal. Using pulses at the control terminal or the gate terminal, we can switch the SCR on. If you look at the device, it has four doped region. First region is P doped region, which is connected to anode. Next region is N, next region is P, and the last region is N, which is connected to cathode. So it has alternating layers of P and N regions. Since there are four regions, there are three junctions. We name them J1, J2 and J3, and the gate terminal is connected to this third P region. Here we connect it to the gate, and this is our control region. Now let us observe the forward bias operation of SCR. If we consider diode, in case of diode, if the anode is at a greater voltage than the cathode, the diode is forward biased and current flows through it. The case is similar in case of SCR, that is when the anode is positive and the cathode is negative. It is called forward biased configuration. Now we are considering we are not using any gate current, that is no current flows through this terminal. So what happens in case of forward bias, this P region is connected to the positive terminal and is more positive than this N region. So this junction J1 is forward biased and a current may flow through it. Similarly, this N region is connected to the negative side, and this P region, so this N region is more negative than the P region, and this is forward biased and the current flows through it. But in this case, this N region is connected to positive side, this P region is connected to negative side. As a result, this junction J2 is reverse biased. As a result, no current can flow through it. Actually, I will be wrong if I say no current can flow through it. A very little current can flow through it because of the minority carriers present in it. As a result, when in forward bias operation, actually the switch is not on and current does not flow through it. So since current does not flow, we call it forward blocking mode of operation. Blocking means the current is blocked. Now, since a very little amount of current flows through it because of minority carrier, we know the current that flows because of minority carrier is called leakage current, and we call it the forward leakage current. Now what happens if we increase the voltage? If we continue to increase the voltage, since this is a reverse bias, what happens when we increase the voltage across reverse bias? The depletion region increases. As we increase the voltage, depletion region gradually increases more and more, and at one stage a time will come when this will go into the breakdown. So at high enough voltage, this junction will go into the breakdown. At breakdown, what happens is high amount of current flows through it. That is, this SCR is turned on, or this is closed circuit, or this is short circuit. So in short circuit condition, what happens is, we can see from the IV characteristics, the voltage is low and the current is high. So the SCR is on and current flows through it. Now let us closely look at the IV characteristics. So at first, when this voltage is low, the amount of current is very low, and which is called forward leakage current, and as we keep on increasing this voltage, leakage current increases gradually, and when we increase the voltage to a certain point, it goes into breakover. So this point is called forward breakover voltage. So what is forward breakover voltage? Forward breakover voltage is the minimum voltage required so that the SCR goes into breakdown in forward bias condition. So the minimum voltage required at which the SCR goes into breakdown in forward bias condition is called forward breakover voltage. Now at forward breakover voltage, the current flowing through it is forward breakover current or IBO, this current. And if more current flows through it, we can see a linear characteristic, that is it acts as a switch. And there is as we can see, the slope is very high. As a result, there is the loss is very low. Now okay, now we can see two more phenomena which are very important. First is latching current and another is holding current. So in order to explain latching current, let us consider a switch. I think we all have used this, and a push button. We all should have used this as well. So what a switch does is, when you press that switch, the circuit is on. If you leave the switch, the circuit continues to remain on. So this is called latched switch. And in case of push button, what happens? As long as you keep the button pushed down, it is on. As soon as you remove your finger, this circuit is off. This is called unlatched operation. So latching current is the minimum amount of current which is required for this switch to turn on and keep on. What this means? What does this mean? This means that we see that the forward breakover current IBO is lower than the actual latching current. So what happens is, if we increase the voltage up to VBO, forward breakover voltage, the SCR goes into the breakdown, and as a result the SCR is on. And if the current of the SCR never reaches as high as the latching current, though it remains on, as soon as we decrease the voltage, again the SCR follows this curve, and as a result SCR switches off. But after the SCR has reached breakover, if we increase the current flowing through it greater than the latching current, the switch is latched. That is, the SCR turns on. Now if the current falls below that current, that is the current flowing through the SCR falls below the latching current, the SCR does not turn off. SCR is still on and it still conducts current. So we see, if the current is the minimum amount of current above which we see the latching action, that is SCR turns on and keeps on, is called the latching current. Now the question arises that how can we turn off the SCR? Since once it's above the latching current, it latches and it just remains on. We cannot turn it off by decreasing the current. Yes, but actually we can. So there is a minimum value of current below which the SCR turns off. This minimum value of current is called holding current. So holding current is the minimum value of current which is required to sustain the SCR on. That is, if the current is below holding current, the SCR will turn off. If after latching operation has already taken place, if the current is above holding current, the SCR will not turn off. So again, I'll be discussing the three important phenomena. The first is forward breakover voltage. That is the voltage above which the SCR goes into breakdown, and the SCR acts as a closed switch. That is forward breakover voltage. Forward breakover current is the minimum amount of current flowing through the SCR which turns the SCR on, or which causes the breakover phenomena. Latching current is the minimum amount of current that is required to turn the SCR on and keep the SCR on. Both the terms are important. This current has to be the minimum current which turns the SCR on and keeps the SCR on. And the holding current is the minimum current required to flow through the SCR which will keep the SCR on. If the current through the SCR is below holding current, the SCR will turn off. So we have discussed this operation for Ig is equal to 0. That is, no gate current flows through the SCR. What happens when the gate current is not equal to 0? Gate current is greater than 0. That is, there is a current flowing through this. So if we provided a positive voltage, what happens? This P side is now positively biased. As a result, what happens? This N side is rich in negative charge. The negative charge will cross the junction and reach here in the P side, and the positive charge or hole of P side will cross the junction and reach the N side. Similarly, positive charge or hole will reach this N side and the negative charge or electron will reach this p side. As a result, the width of this p layer will keep on decreasing. As we increase the gate current, the width keeps on decreasing. Since when the width decreases, the current will easily be, the carriers will easily be able to drift. So the holes from the anode will easily be able to drift to the cathode, and electrons from the cathode will easily be able to drift to the anode. So the more we increase the gate current, the thinner this layer is, and as a result, more current flows through it, or easily it goes into the breakout. If we look at the IV characteristics, we can see that the shape of IV characteristics is the same. Here, when there is no gate current, the breakover voltage is at much greater voltage. But when we apply gate current, that is when we apply Ig1, small amount of gate current, the breakover voltage decreases. When we apply a greater value of gate current, breakover voltage decreases further. That is, if we apply gate current, if the voltage across the anode and cathode is low, even in that case, this SCR will turn on. One thing to note is that the phenomenon of latching current and holding current remains the same irrespective of whether we apply gate current or not. That is, no matter if we apply gate current or not, the latching current of this SCR will be constant. The holding current of this SCR will also be constant. After our discussion of the forward bias operation, we will discuss about the on and off states of SCR as a switch. So this curve over here is called the on state, and this curve over here is called off state. That is, when the SCR is off, it will follow this curve, and when the SCR is turned on, it will follow this curve. To explain it further, as we can see that when the breakover does not happen, the SCR follows this curve. That is, the IV characteristics of SCR is like this. When the breakover happens and the current is equal to the breakover current, and if the current is in somewhere between the breakover current and the latching current, or somewhere between the breakover current and the holding current, it will be on. The SCR will be on, but the operation will be unlatched operation. That is, in this case, difference in current will follow this curve as long as it does not go below holding current. But what happens is, if we decrease the voltage across the SCR, the IV characteristics will follow this curve and not this curve. That is, if we haven't reached the latching stage yet, if we decrease the voltage, it will reverse the breakover situation and it will follow the forward blocking mode. Now if you consider we have gone through the breakover and we have increased the current to a level greater than the leakage current, greater than the latching current, then what happens is the SCR is latched. That is, it is permanently turned on. So since it is permanently turned on, then no matter how much we change this voltage, that is voltage across the anode and cathode, the IV characteristics which it will follow is this, that is a straight line. It will follow this straight line. If we increase the voltage, the current will be rising. If we decrease the voltage, current will be falling. But this phenomena will keep on occurring as long as the current is not below the holding current. When we have decreased the voltage low enough that the current is below the holding current, then the SCR turns off and it again starts to follow the off state. Now what happens if the SCR is in reverse bias? That is, the negative terminal of the voltage source is connected to anode and the positive terminal is connected to cathode. So when this happens, the P side is negative and the is more negative than the N side. So this is reverse bias and no current can flow through it. Similarly, this N side is more positive than P side. So this is also reverse bias and no current can flow through this junction. As a result, what it happens, no matter how much Ig or the gate current we push through, there are two reverse biases, and as a result, no current flows through the SCR. Actually, a very little current flows through the SCR, which is because of the minority carrier, and that current we call reverse leakage current. And this mode of operation is called reverse blocking mode. So as a result, in reverse bias operation, no current flows through the SCR. Now, if we keep on increasing this voltage source at one stage of time, since there are two reverse biases, at one stage of time, both the reverse biases will undergo breakdown. When it undergoes breakdown, reverse breakdown voltage, a high current flows through the SCR and the SCR burns down. So this is the reverse bias operation of SCR. Generally, we always use SCR in the forward bias, and we use gate current to control the to switch on the SCR. And the method of switching off the SCR is we make sure that the current through the SCR is below the holding current so that the SCR turns itself off. This is it for today's lecture. Thank you so much.